The title of our final project is Enhancing Role-Play Memory in Large Language Models with Retrieval Augmented Generation, a case study on the Harry Potter corpus. First, let me introduce you to the background. Role-play task. In the context of LLMs, role-play refers to a task where the model is asked to simulate a specific character, persona, or identity and respond in character throughout the interaction. We identify two key characteristics of role-play task. The first is role consistency. Role-play task requires the model to consistently maintain the assigned character throughout the interaction. This includes producing reactions, tones, and language that align with the character's identity and behavior. For example, if we say we want the LLM to role-play Harry Potter, it should sound like Harry Potter. The second characteristic is called memory awareness. Basically, the model should be equipped with relevant background knowledge and be able of recalling and referencing specific memory appropriately during the entire procedure of the conversation. So we identify one key problem of doing it with the traditional LLMs. Namely, traditional LLMs are constrained by their finite context window, which limits the amount of prior conversation or task-relevant information they can process at once. Such architectural limitation leads to a lack of long-term memory, making it difficult for the model to recall earlier interactions or maintain consistent behavior over time, especially in tasks like role play. And our proposed solution is we use retrieval augmented generation. By combining information retrieved in real time with language generation, RAG allows models to dynamically access and integrate external knowledge throughout interaction. This approach can improve the model's ability to generate context-aware and consistent responses. Next part, we talk about methodology used in this project. The first part of methodology is embedding models. Embedding models are a type of machine learning model that transform high-dimensional sparse data like text or images into lower dimensional dense vector representations called embeddings. These embeddings are numerical representations that capture the semantic meaning, structure, or relations within the data, allowing for efficient computation and better generalization. In our project, the model we use is text embedding ADA002. It is the most advanced embedding models from OpenAI. We could see that even compared with task-specific models, ADA002 performs well across all four tasks, which are text search, code search, sentence similarity, and class classifications. For vector library, we use FAISS as our format. FAISS, Facebook AI Similarity Search, is an open source library developed by Meta for efficient similarity search and clustering of dense vectors. It is widely used to search for similar items in large-scale datasets. This image illustrates the workflow of FAISS for similarity search in a vector library. First, media items are processed into dense vector embeddings using an embedding model, capturing their semantic features. These embeddings, represented as high-dimensional vectors, are organized and stored in FAISS index structure in memory for efficient retrieval. When a query is later provided, it is also converted into a vector and compared against the index vectors using a similarity matrix. Fice efficiently retrieves the nearest neighbors, returning the most relevant results. For this part, we talk about the pipeline of our work. Our work consists of three parts. The first part is about memory library construction. First, we use embedding models to transform Harry Potter memories to vector representations. Next, we index and store the vectors into library using Fice. The second part is to establish the baseline results for LLM without RAG. First, we use Gemini to generate question-answer pairs. Then, we ask LLM models to generate answers with these pre-generated question queries, and finally we analyze the outputs. The third part, we evaluate the performance of our RAG agent. Our RAG agent starts with retrieve the related memory in the memory library for the specific question. We then combine the selected memory and question into one query. Finally, we ask LLM with this new memory question query and proceed to analyze the outputs. Here, we show an example of our dataset. Next, we talk about the evaluation we have done. We focus on two main tasks to evaluate our RAG-based system. The first task is called memory provenance validation. This task deals with how we handle different types of memories. Basically, there are two types of memories. The first type, we call it Harry present memories, which are events directly experienced by Harry Potter. The second, we call Harry knowing memory, which are information learned secondhand through other characters. So, for example, when asked, do you remember? The model should not use Harry knowing memories as query results in the prompt, because this refers only to the first-hand experiences. Basically, this task measures the model's ability to distinguish between first-hand and second-hand memories. Next, we have task 2, temporal compliance. This task is about making sure the model stays within the correct timeline. LLMs are pre-trained with all 7 Harry Potter books, so naturally, they can generate information that goes beyond the scope of what Harry knows by the end of book 5. What we need is for the model to accurately recall events from book 1 through book 5, while rejecting content from books 6 and 7. This task is all about making sure the model respects the timeline and don't overstep what it should not know at a given point. Next, we show the results. We see from the table that in terms of overall model performance, RAG retrieve augmented performs better than standard RAG. Both of them are better than the baseline. This is intuitive. As for task performance, we saw that models perform better on the memory provenance validation task than on the temporal compliance task because the latter is more difficult. In task 1, the prompt explicitly tells the model what kind of memories it's working with. It knows whether the memory is something Harry experienced firsthand or just heard about secondhand. But in task 2, the model has to infer whether a piece of information violates the current timeline. This kind of temporal reasoning is much more difficult. So, the baseline model performs poorly on the temporal compliance task also. This is because it is portrayed on the entire Harry Potter series, so it tends to include facts from all 7 books, even when those facts are beyond what Harry should know by the end of Book 5. Namely, the portrayed model is omniscience. As a result, the model frequently answers yes to out-of-scope questions. We see a large number of false positives in the confusion matrix. For the memory provenance validation task, we see that precision is higher than recall. That's mainly due to class invariance in the dataset. There are a lot more positive samples than negative ones, so the model tends to be more conservative in its predictions to ensure a higher overall accuracy. So here we draw the conclusion for this case study. First, across both tasks, we can observe a clear performance hierarchy. IEG with retry performs best, followed by standard IEG, and finally the base model. This pattern reflects the complementary strengths of the retrieval mechanism and the retry mechanism. Retrieval helps the model ground its answers in relevant parts of the external memory, which improves contextual accuracy. On top of that, the retry mechanism allows the model to make multiple attempts, helping reduce missed answers and false recalls. These two components lead to better memory alignment, more selective responses, and stronger control over temporal consistency. Overall, our findings confirms the effectiveness of the IEG-based design in the role-play task. That is the end of our presentation. Thank you.